Hey guys, good afternoon.
How's it going, Dr. Tran?
Good, how are you?
Doing well. Are we doing the ANSYS lab today or next time?
So the next ANSYS activity isn't planned for a while now. So we're gonna stick with the theory for a while. I think the next time we do an ANSYS activity will be in week 6, actually.
Ah, gotcha. Okay.
Mhm.
I had a quick question.
Yep. What's up?
So for assignment or homework number one, the
Mhm.
trust one,
Yep.
on the actual document, it says that it's due today.
Oh,
Yeah. I mean
I will.
on the canvas it said it's due, I think, like March or no,
Mhm.
it's the 23rd, I think, something like that.
Oh yeah. Okay.
But I just
I
wanted
need
to
to
make sure.
I need to fix that. Yeah. Thanks for letting me know. It's definitely not due today.
Okay, just okay. And then we're going over the Truss notes today, right?
Yes.
Okay.
Okay. I'm gonna.
All right, it's 4 o'clock, so let's go ahead and get started. Good afternoon, everyone. How's everyone doing today?
Good
I'm
afternoon.
doing well.
Good. Good. Yeah, it's our third week already, so semester is definitely in full swing. Okay, so we have our first assignment that's due today. So that's the first ANSYS activity. And so that's the one we did last Tuesday, which is the plate with the hole, right? So I know that there were some, some people had some issues with the software versions, but was everyone able to at least finish the activity?
I finished it last night.
Okay,
Yeah.
great. So that's due tonight at 11:59. So you still have some time to finish it up. And so if you haven't turned it in, definitely make sure you do that. And so I know that there's some questions about, how you submit the assignment. And so for the assignment, and this goes for all of the ANSYS assignments. I don't need your ANSYS files because I'm not going to open up, 40 different ANSYS files, right? So all I need is basically just screenshots of the results. So when I ask you for, the color contours for the results, it would be best if you just take a screenshot and then put that into a single document. And so, you can either use the screenshot feature within ANSYS, or you can just take a screenshot just from your desktop too. And either of them works. Okay.
Do you want the legend in that screenshot?
Yes, that would be great. Yeah.
Cool.
Yeah. So just whatever's in that view would be good. Yeah. Okay. So it looks like, okay. So your ANSYS isn't working. Okay, so if you're having trouble with or if you haven't gotten ANSYS to work up to this point, either on your computer or through the virtual machines, just let me know. Preferably send me an email just so I can see it after the class. And just because this is the first assignment, and if you haven't gotten ANSYS to work at this point, I can give you guys an extension on that. But if you have ANSYS working and you can get it in by today, that would be best because I'd like to grade that sooner than later. Okay.
Good question.
Yep.
So I know that when you're doing the tutorial with us, some of us had the licensing for this certain program would be valid only for 20 days.
Yep.
Do you ever, or are we going to continue using that part, or?
Yeah, I'm hoping that was just a mistake, but for the next activity, I haven't gotten around to it yet just because I've been working on some other stuff, but I need to download the latest version that probably a lot of you guys are working on, which is 2021 ANSYS. And so if I'm getting the same thing, and I'll work something out with with the versions, and I'll send an update to everyone just to fix that, because we're definitely going to need ANSYS for more than 20 days from here.
Okay, cool. Just double check. Thank you.
All right. So go ahead.
Also, I had a question about problem 4, part D. Do you want us to just fill in the matrix? Or?
Yeah. So just fill in the matrix, write it down on a piece of paper, and then and scan and upload that. So yeah, there's nothing to solve in that one. It's just practice kind of assembling the global stiffness matrix.
Yeah. Thank you.
Yes. So if you can submit just take screenshots and put it on a single PDF, that would be the best way to submit this. Yeah. And I don't need any MATLAB files or anything like that too. So just you can just give me just the final results from that. Okay. Are there any other questions on that activity or anything that we covered last week that I can answer before we get started?
Yes. One quick thing, Professor, just
Sure.
to make sure. The original mesh size was 5 millimeters, right?
Correct.
Okay, cool. Thank you.
Yep. Yeah, and then for the other activities, I want you to do a finer mesh. So do one at 2.5 millimeters, and then a coarser mesh. So you make the mesh bigger than that. So you should have three for the mesh parting for the meshing part. You should have 3 different meshes and 3 different simulation results. Yep. Okay. All right. So so we're moving on to a new set of lecture notes today. And so we're going to be starting lecture note 03, which is on truss equations, right? And so this is basically going to be an extension over what we did last Thursday, which was the direct stiffness method. Okay. Okay. And so just as a reminder, what we started last week, we're going to continue on for the next couple weeks, and it all has to do with what's called the direct stiffness method. Okay. And so the idea with the direct stiffness method is that, I'll give you guys some structures, right? And you're gonna be able to break it down into elements and then solve it using the finite element method. Okay. And so last week what we did was springs, right? And what we saw for springs was that it had a 2x2 element stiffness matrix, right? So this is the element stiffness. Right. And so it's 2x2 matrix that looks like this, right? Right. And so on the diagonals, we had a positive value of K. On the off diagonals, we had a negative value of K, right? Where K here, K is just the spring constant for the spring. Right. So there's our spring. Right. And the way that we use these element stiffness matrices is to basically compute how much the spring is going to deform or how much it's going to displace when we expose it to some forces. And so last time, we had systems that might look like this, right? So maybe we had, multiple springs. So here I have 3, right? And so if we pull the spring, with the force F, what we can do is we can compute, how all of these different nodes displace, right? Right. And so if we pull a spring assembly, with the force F, we'll be able to compute how all the nodes displace based on our direct stiffness method, right? And so our in the end, what we solved was a system of linear equations, which look like this, right? Right. Where big K here, this is our global stiffness matrix. Okay. D right here, this is our vector of displacements. Okay, so that's what we're solving for. And F here, F represents any kind of forces and boundary conditions that we're applying on our system. Right? Right. And so once we form the linear system, then we just plug it into MATLAB, and then we just solve the system from there. Okay. All right. And so this, what we're going to do this week is we're going to extend this this methodology to handle different kinds of elements, right? Because even though we started with a spring, springs are great. Springs are fine because they have just one constant, but you don't see that many springs out there in reality all that much, right? So you don't see, our engineering building isn't held up by springs, right? It's held up by, structural beams, structural truss members, structural frame members, right? And we'll see. So this week, what we'll see is we'll extend this methodology, and so we're going to be using the same methods, but instead of this element stiffness matrix, we'll have a different one to represent all the different kinds of structural elements that you can have, in a structure. Okay. Okay. Any questions on that? Okay. All right. So let's start with the element stiffness matrix for a truss element. Well, I guess first of all, let's start with what is a truss element, right? And so a truss element is another name for that's given a lot is a bar element. Okay. So sometimes you'll see those two words used interchangeably, but they both mean the same thing. Okay. And so visually, usually is given something that looks like this. And so they don't have to be cylinders, but schematically we usually assume that it's so. Okay. And what's unique about truss elements is that they're loaded axially. Okay. And so what that means is that any forces that they experience are just going to either be compressive forces or tensile forces. Okay. And so visually that would look something like this. So we have kind of the long axis of the truss going from left to right. Then let's say if we want to put the bar in tension, we would apply a force in the left and right on the bar. So it just kind of pulls that way like that, right? And if you do that, then the bar is also going to stretch, right? Right. And so the displacements are also going to be axial, right? So they're either going to cause the element to elongate or it's going to compress. Okay. And so when we say truss elements, that's all we mean is that the forces that are acting on it and also the displacements are limited in the direction of whatever the truss element is. Okay. Okay. And so let's give this bar some properties, right? And so what are the physical properties that determine how much the truss is going to displace? Right? Okay. And so first thing that we have is the Young's modulus. And so usually we give that symbol capital E, right? And so Young's modulus is a property of the, of whatever material it's made out of. So it tells you how strong that material is, right? And so steel is going to have a certain Young's modulus. Iron is going to have another one. It really depends on what material that you're using. Okay. There's also some geometric properties. And so the bar is also going to have a length, right? So the length is simply just how long the bar is. Right? And then one other property that we're going to need is the cross-sectional area. Okay. And so usually we give that the symbol A. Okay. And so these are the properties that we'll be working with for this bar. Okay. Okay. And so let me label a couple more things before we get started with the derivation. Right? And so we're also going to need to label the nose. Right? We'll call this side 1. We'll call this side 2. Right? And just for the sake of having things all pointing in the same direction, we'll call this D1. We'll call this D2. Okay. And so I'm labeling these displacements such that their positive direction is pointing that way. I know this diagram looks weird because we're pulling node 1 to the left, and so you would think node 1 would displace to the left, but I'm just kind of labeling these displacements as going positively to the right. Okay. In reality, we know that D1 is going to go to the left because we're pulling it that way, but these directions here are just for convention. Okay. Okay. And so that's our truss element. And so now let's start talking about its stress strain behavior. And so the stress strain relationship for a truss bar like this is going to look like this. And so we have the stress in the bar. So that's sigma. This is going to be equal to the Young's modulus multiplied by its strain. Okay. Okay. And so this is just a simple, stress strain relationship. So we say that the stress is linearly related to the strain, and the slope of that line is going to be the Young's modulus. Okay. So it's a very simple kind of linear isotropic material. Okay. All right. Any questions on this so far?
No questions here.
What's that again?
No, not for me.
Okay. Okay. Great. Okay. And so this formula is going to be our starting point right here, but we need to kind of fill or kind of replace some of the terms here. Okay. And so Young's modulus is okay. And so because we already have that, but we don't have, an expression here for the stress or the strain. Okay. And so let's replace these guys with expressions that, of what we're given in the problem. Okay. And so let's start with the stress. All right, so the stress here, if you recall kind of the definition for stress, is nothing more than just a force distributed over an area, right? Okay. And so, because, the units for force are usually in pascals, and pascals is, a Newton over an area, okay? All right, and so we can replace this expression for stress with some parameters that we actually have from our diagram, right? And so let's look back at our diagram here and let's write down any of the forces that we see, right? And so the only force that we see in this case is the tensile force, right? And so let's use that. And then the area that is being distributed over is the cross-sectional area of our bar, right? And so we can replace this, the sigma for stress here with just T over A. Right? Right? And so if we replace sigma in the equation with this, what we have is T over A is equal to E times epsilon, okay? And then if we multiply both sides by A, right? We multiply both sides by A, then we have is T is equal to AE epsilon, okay? All right. And so we're getting warmer. And so now that we've replaced sigma, now we put this equation in terms of, at least things that we recognize, okay? All right, and so now let's work on the strain. All right, so let's recall our definition for strain here. And so strain is a relative change in length of the bar, okay? All right. And so kind of the formula definition for strain would look something like this. And so usually we compute strain as a derivative of the displacements. Okay. And so I know it's a little bit confusing because I use D here, but this D that's in parentheses here is displacements. Okay. And so we can approximate this derivative according to the displacements that we have in our diagram, right? Because we know from our diagram here that we are interested in the displacement of node number 2, and so that's why we have D2 there. And we're also interested in the displacements for node 1. Okay, so that's why we have D1. And so the total change in length, you can take this to be D2 minus D1. Right? Right? And so this and so that difference right there, D2 minus D1, represents the change in length of the bar. Okay. All right. And then since the strain here is a relative change, let's divide this by the original length. Okay. And so this L right here is our original. This L right here is our original length. Right. And so let's go ahead and plug this guy in for epsilon, and then we'll have our stress strain relationship in terms of parameters that we have in the problem, right? And so right now we have T is equal to AE times epsilon. So epsilon is going to be D2 minus D1 divided by L. Okay. Let me rearrange these terms a little bit just to make it a bit easier to work with. And so I'm going to pull the L out from there, right? So we have AE over L times D2 minus D1, okay? And this here is a formula for the the relationship between the tension and the two nodal displacements, okay? Okay, any questions on this so far? Okay, all right. And so now that we have a formula here for the tension, let's use that as our baseline to compute the nodal forces. Okay, and so let me draw our truss here again. Right? And we know on this side is node 1, and here's node 2. Okay, and then we're saying that the displacement at node 1 is going to be D1, and the displacement at node 2 is going to be D2. And so in addition to this, if you remember from how we derived the element stiffness matrix for a spring, what's causing these displacements are forces at these nodes. Okay. And so F1 and F2 right here are forces applied at nodes. Okay. Right. Okay. But we also just got done computing the value for T, right? Because remember, we're stretching this bar in tension, right? And so we can have a T on a minus T on the left side and a positive T on the right, right? And so these tension forces that we have here are actually exactly the same as F1 and F2, right? And so what we can say is that F1 is going to be equal to minus T, right? So remember, F1 represents all the forces that we're applying on the first node, right? And so since we're just applying a force of T in the negative direction, we can say that F1 is just equal to minus T, right? And so let's go ahead and plug in our equation for that. And so if we use our equation on the previous slide, we can say that F1 is going to be equal to minus AE over L times D2 minus D1. And then let me just rewrite this. So this will be, I'll distribute the negative on the inside. So this will be AU over L times D1 minus D2. Okay. This is F1. Right. And then similarly, we can write the equation for F2. And so F2 is simply just going to be T, right? Because here F2 and T are in the same direction, so we don't need to add a negative, right? And so F2 is going to be AE divided by L times D2 minus D1, okay? All right. Okay. And so now we have two equations, and what these two equations represent is a relationship between the nodal forces and the nodal displacements, okay? Okay. And so this is just like what we had with the spring, right? So for the spring, remember, we use the spring constant to relate the nodal forces and the nodal displacements, right? And so what we can do at this point is take these two equations and then pop them into a matrix. And then this matrix will form our element stiffness matrix for a truss. Because remember, our element stiffness matrix is is exactly that relationship between the forces and the displacements, but placed in vector form. Okay. All right. Any questions on this before I write down the element stiffness matrix for a truss? Okay. All right. So let's go ahead and do that. Right. All right, so just like the spring, we're going to have a vector here for the forces. And so we're going to have F1 and F2, okay? We're going to have a vector for the displacements, right? And so we have D1 and D2. And then we're going to have our element stiffness matrix here in the middle, right? And so let's write down the first equation first, right? And so the first equation says that we have F1 is equal to AE over L times D1 minus AE over L times D2, right? And so if we pop these coefficients into the matrix, what we have is AE, positive AE over L, right? And then minus AE over L, okay? And so that's the first row in the matrix, because if you multiply this first row in the matrix by our D1, D2 vector, you're going to get the exact equation that we got on the previous slide, right? And then next, let's write down the equation for F2, and then F2 is going to be minus AE over L times D1, and then positive AE over L times D2, okay? And those are just the coefficients from our second equation for F2, okay? And so, we can put this in a slightly simpler form because writing AE over L over and over again is a little bit cumbersome. And so let's factor out AE over L, okay? And so what we get is F1, F2 is equal to AE over L times the matrix 1 minus 1 minus 1, 1 times D1 and D2, okay? And then this guy right in the middle here, this matrix, this is our element stiffness matrix for a truss. Okay. Okay. Let's compare this to our element stiffness matrix for a spring, right? So for a spring, remember our element stiffness matrix look like this, right? And so we have K, minus K, and K, right? And so, just like we did up here, we can factor out K, and so we have K, 1 minus 1, minus 1, 1, okay? Right, so this is element stiffness matrix for a spring. Okay, you can see that they look very similar. And so the only difference in between them is that for a truss, out in front, we have AE over L, and then for the spring constant, we have just K, which is the spring constant, okay? And so that's no accident, right? And so what we can basically say is that AE over L, this is almost like an effective spring constant for a truss member. And so if we think about it like that, we'll be able to solve truss problems in exactly the same way that we solve spring problems, okay? It's just the only difference now is that instead of using K, the spring constant, we have to kind of compute it using the Young's modulus, the area, and the length of the truss, okay? Okay, any questions on this before we jump into an example? Okay. All right, so let's do an example to show how this works in action. Okay. All right. And so let's consider the following truss assembly. And so this will be an assembly of 3 different trusses. And so on one wall, we're going to have a fixed wall here. And then the other wall is actually going to be fixed as well. Okay? And so you can see here I have 3 lines, and so those 3 lines are going to be our 3 elements. And so we have element A on the left, element B in the middle, and element C on the right. Okay. And so those are the element IDs. And so let me go ahead and label our nodes. Right. And so our nodes are going to be labeled 1, 2, 3, and 4. Right. Okay. Let's define the length of each of the elements. And so we'll say that each of these elements here are 30 inches long. Okay. And so they all have the same length. And so overall, we have a length of 90 inches. Okay. And let's start defining some of the material properties. Okay. And so we'll say that A and B are identical. And so elements A and B will have the same properties. And so we'll say that these guys have a Young's modulus of 30 times 10 to the 6 psi. Right. And then their area is going to be 1 inch squared, or 1 square inch. Okay. All right. So A and B are identical, so they have both of those same properties. But element C here will be different, right? It's made of a different material, and it's a little bit bigger. Okay. All right. And so element C, let's say that we have a Young's modulus of 15 times 10 to the 6 psi. Okay. And our area is going to be 4 square inches, okay? Or 4 inches square. Okay. All right. So those are all the properties on the truss. Okay. We can see from this diagram here that nodes 1 and 4 are fixed because they're attached to a wall. And so the last thing that we need here is some kind of forcing. And so let's say that we're going to grab this bar in the middle at node 2, and we're going to pull it to the right with a force of 3,000 pounds. Okay. Right. And so there's our problem. And so from here, what we want to do is we want to use the direct stiffness method and to compute the nodal displacements. Okay. And so now that we've kind of written down everything about the problem, we can start solving this guy. And so we're gonna follow the exact same procedure that we used last Thursday, right? And so if you remember from our spring problems, the first thing that we have to do here is to compute, first we have to compute all of the element stiffness matrices, right? Okay. All right. And so we have three elements here. So we're gonna have 3 element stiffness matrices. And so the stiffness matrices for elements A and B are going to be the same because they're identical. And so let's go ahead and write that first, right? And so we'll call this one K A, KB, right? And so if we plug in if we write down our equation for the element stiffness matrix for a truss, we know it's going to be the area of the element times the Young's modulus divided by the length times 1 minus 1 minus 1 and 1, okay? Let's go ahead and plug in those, the numbers. And so if we plug in 30 times 10 to the 6 psi for the Young's modulus, we plug in an area of 1 inch squared, and the length we know is 30, right? Then what we get is 10 times 10 to the 6, 1 minus 1 minus 1 and 1, okay? Oh. Right, so that's the element stiffness matrix, but we have to write down which nodes that these guys act on, okay? And so I'm gonna, they're both gonna have the same numerical values, but, we also need to write down what, nodal displacements that they act on so that we can put them into the global system in the correct places, okay? All right, any questions on this so far?
So will our matrix ever change?
You mean the element stiffness matrix?
Yeah.
Yeah, so this format is always going to be the same. So it's always going to be AE over L times, this 1 minus 1 minus 1 matrix. It's just the numbers that you plug in for the AE over L is going to change. Right?
But the 1 over -1 matrix won't change?
Yep, those will always be the same.
Okay.
When we get to 2D, we'll see how this expands into 2D, and that's when things start to get pretty complicated. But for 1D problems, it's always going to be this 1 minus 1 minus 1 and 1.
Okay.
Yeah. Okay. And so just so we know that we can assemble it in the right places, let's write down the element stiffness matrices for A and B. Okay. All right. So we know Ka is going to be 10 to the 6 times 1 minus 1 minus 1 and 1. Okay. And then from our diagram, we know that element A is going to be acting on D1 and D2, right? Because it has node 1 on the left and then node 2 on the right. Okay. Right. And then KB is going to have the same numerical value, so it's going to be 10 times 10 to the 6. Okay. Except it's going to be acting on nodes 2 and node 3. Okay. Okay. So that's elements A and B. And now let's write out the element stiffness matrix for element C. Right? And so we're going to use the exact same equation, except we're going to use the properties for C, right? And so for C, if you remember, it has half the Young's modulus, and so it only has 15 times 10 to the 6 psi, but it has 4 times the area. Okay. So it's going to be AC, EC, LC times 1 minus 1 minus 1, 1. Okay. And so if we plug in all the numbers for that, what we get is 2 times 10 to the 6. Okay. 1 minus 1 minus 1 and 1. Right. And then the nodes this is going to be acting on is going to be nodes 3 and 4. So we have D3, D4. Okay. All right. And so these are our 3 element stiffness matrices right here. And so now that we're done with this, we're going to assemble this into the global system. Okay. And so our global system here is going to be a 4x4 because we have 4 nodes, right? And so let me label the columns here as well. Right. And so there's our matrix, okay? And so now we need to start filling these guys in, right? And so just like, just like we did before, we're going to fill these into the locations based on which nodes that they're acting on, right? And so let's start with A, right? And so element A here is acting on nodes 1 and 2. And so we need to put this into the nodes, our D1, D2 rows and D1, D2 column, right? And so that's going to correspond to this area right here. Okay. Right. So we kind of blocked off this this section of the matrix, and that's for Ka. Right? Next, let's do Kb. And since we know that Kb works on nodes 2 and 3, we're going to block off the 2, 3 section of our global stiffness matrix. Right? And so that's going to be just like this. Okay. And you can see here that we have one overlapping part. And remember, whenever we have things that overlap, we simply add their values together. Okay. All right. And so finally, let's do element C. And so element C I'll do in blue, and that acts on nodes 3 and 4. And so that's going to be just like this. Right. And so element C is going to go in that area right there. Okay. All right. And so once again, we have an overlap on the D3 slot. And so we're going to add our components there. And then everywhere else that's not included, we're just going to throw zeros in there. Okay. And so let's start filling in some values here. So let's start with element A. And so element A, we have 10 to the 6, minus 10 to the 6, minus 10 to the 6, and 10 to the 6. Okay. Next, we have element B. And so numerically, it has the same values, but it's just kind of shifted over, right? And so on the overlap part, you can say, well, we're going to add 10 to the 6 there. Then we're going to have a minus 10 to the 6, minus 10 to the 6. Okay. And then positive 10 to the 6, right? And then finally, for element C, we're going to fill those in right there. But the numerical value for element C is going to be 2 times 10 to the 6. Okay. And so we're going to add plus 2 times 10 to the 6, minus 2 times 10 to the 6, minus 2 times 10 to the 6, and 2 times 10 to the 6. Okay. All right. And so if we simply add up the overlap parts, this guy right here is going to be 2 times 10 to the 6. And then for this overlap part right here, we're going to have 3 times 10 to the 6. Okay. All right. And so there's our global system. Okay. And so we've done it, just by adding our element stiffness matrices, just like we've done before, right? One thing I'll comment on here. So, whenever you have parts of your element stiffness matrix overlap, that generally means that those two elements are sharing the same node, right? And so let's look at this first overlap region between elements A and B, right? And so those overlap on the D2 slot, right? And so what this implies here is that elements A and B are sharing node 2. Okay. And if we go back to our diagram, you can see that's exactly true, right? So element A, ends on node 2 on the right, and element B starts on node 2 on the left. And so the fact that they both share that node means that they're going to have some overlap on the element stiffness or on the global stiffness matrix at node number 2. Okay. Same thing can be said about elements B and C. And so elements B and C, they both overlap on node 3. And so you're going to have some overlap there on node 3. Right? And that's exactly what you get right here. Okay. All right, so just kind of something to keep in mind as you're doing these problems, because you know, once we start doing more complex 2D systems, this is kind of a good sanity check that you can do to say that, you know, am I overlapping in areas that make sense, right? So because if there's overlap, that means those two elements should share a node, and if that's not the case, then you know, you might want to go back and check your work a bit. Okay. Okay. And so we're not done with this system yet, because our next step here is we're going to need to apply our boundary conditions. Right. And so we have three boundary conditions here. So we have a fixed support on node 1, a fixed support on node 2, and also a force on, a fixed support on node 1, fixed support on node 4. So those are the ones at the two ends of our domain. And then we also have a force that's being applied on node 2, right? And so that's this guy right here. Okay. And so we need to account for all of those forces, all of these boundary conditions, right? And so just like we did with the spring, let's start with the force boundary condition, or a Neumann one, right? And so if you remember from our spring, whenever we have a force boundary condition, all we have to do is just kind of plop that into the right-hand side matrix on that appropriate row, okay? And so since in this case we are applying a force on node 2, we're going to put that force value here on this row right here. Okay. And so since we're applying a force of 3,000, then we're going to put a 3,000 in there. Okay. And then all the other forces are 0. Okay. All right. Any questions so far on this?
Weird question. Let's say node 4 was let's say this was hanging from a ceiling.
Mhm.
What our force would be, like for example, for node 4, since it would be hanging with a mass, would it be like the mass plus gravity, or multiplied by gravity, so the weight of that?
Yeah, so weight is kind of something that's a little bit different. So weight is something that's actually felt throughout the entire structure. And so you know, if you're considering kind of the weight of these bar elements, that actually gets incorporated, you know, into this matrix right here.
Yeah.
And all of them would have kind of the same contribution, you know, because they would all have kind of roughly the same weight.
Okay.
And so for now, we're kind of ignoring that. We're kind of ignoring that, you know, the fact that these guys have weights. But if you had kind of a weight on the bottom of node 4, so you have like a truss structure, and you have like maybe it's carrying a big load on the bottom,
Yeah.
then you would apply that vertical load on node number 4.
And I was gonna think about that, but just wanted to see like how it would affect the rest of the system, or if it would just affect one node. Okay, thank you.
Yeah. So you really have to see where the load or where the forces are being applied, and then apply that on the correct row of the global system.
Okay, thanks.
Mm-hmm. All right. Any other questions before we apply the fixed support boundary conditions? Okay. All right. And so now we need to apply the fixed support, right? And so remember, the way that we apply the fixed support is that we actually modify the matrix on the left. Okay. And so since in this case we have two fixed supports, we have a fixed support on node 1, and we also have a fixed support on node 4, right? We're going to be modifying these rows in the matrix right here, right? And so let's start with node 1, right? And so to apply the fixed support on node 1, all we're going to do is we're going to change this row to all zeros, except for the diagonal term. So except for the D1 term, and so we're going to make that a 1, just like that. Okay. And then to apply the boundary conditions on node 4, we're going to do the same thing. So we're going to change the entire row to zeros, but we're going to change the diagonal term to 1. And so in the fourth row, the diagonal term is going to be the fourth column, right? So we're going to put 1 just like that. Right. And so now that we've done all that, now finally this matrix here is ready to solve. Okay. And so at this point, you've done all the work that you can by hand. I mean, technically you can solve this, by hand from here as well. But it's usually not fun to solve a 4x4 system of linear equations. So here we can plug this into MATLAB. And use that to solve for the displacements. Okay. All right. And so since this is an in-class example, I've already done that for you, right? And so after plugging that into MATLAB, we get the following solutions. And so first thing you'll notice from MATLAB, if you set this up correctly, is that D1 should be 0 and D4 should be 0, right? And that makes sense because that's where we applied our fixed supports, right? And so if you're applying a fixed support somewhere and you get a non-zero displacement, then something went wrong, and you should probably go back and check that. Okay. All right. And so D2, this is the node where we applied our force, and when we solve it, we're going to end up with the displacement of 0.0018 inches. And then node number 3, which is also hanging, we end up with the displacement of 0.0006 inches. Okay, and these are our solutions. Okay. Okay. So that's how we do truss problems in 1D. So you can see the process is exactly the same as our spring problem. It's just that the way we compute the element stiffness matrix is different here. Okay, because we have to take instead of a spring constant, we have the area, we have the Young's modulus, and we have the length. Okay. All right. And so now that we have this solution here, we can actually go a step further and compute the reaction forces. Okay. And so the reaction forces are going to be nothing more than just the forces that are being applied on the nodes of our structure. Right? Because even though we're applying this force here and we're applying our boundary conditions, this truss we're assuming is in static equilibrium. So in fact, it's not moving, right? And so there has to be some forces that are applied on the nodes of the system that basically keeps this guy in static equilibrium. Right? And so to do that, and so to compute these reaction forces, what we need to do is we need to take our displacement solution and then plug it back into our global system. But we need to plug it into the global system before we apply the boundary conditions. Okay. Okay. And so this is before we plugged in, the Neumann boundary condition on the right, and before we changed the rows, right? And so if you remember, our global system for this guy looked like this, right? So we had 10 to the 6th minus 10 to the 6th, and then 0 and 0. And we had minus 10 to the 6th, 2 times 10 to the 6th, minus 10 to the 6th, 0. Then we had 0, minus 10 to the 6th, 3 times 10 to the 6th, minus 2 times 10 to the 6th, okay, 0, 0, minus 2 times 10 to the 6th, then 2 times 10 to the 6th. Right? Then we had D1, D2, D3, and D4, right? Then on the right-hand side, we had our forces, right? Okay. And so to compute when I said, when I asked you guys to compute the reaction forces, what I'm actually asking you for is this guy right here on the right, okay? Because what you can do is you can take our solution that we just found, plug that back into here, and then perform the matrix multiplication, right? And so again, you can definitely use MATLAB for this. MATLAB will help you compute those forces or do the matrix multiplication pretty easily, and then you'll be able to compute all of these guys. All right, any questions on this so far? Okay. All right, so then if we plug all of those in, then we get the following reaction forces, right? And so we get F1 is equal to minus 1,800 pounds, right? F2 is going to be 3,000 pounds. F3 is equal to 0 pounds. And F4 is going to be equal to minus 1,200 pounds. Okay. All right. And so these are the forces that are being applied at every single node in our truss system here. Okay. All right. And so just to kind of double check that your solutions make sense, here's kind of what you can do. Right? And so let's start with F2. Right? If you remember from our problem, node number 2 is where we applied our load of 3,000. Okay. And so when we compute the reaction forces, you should see that you get the exact same thing back, right? And so whenever you have an applied force, whenever you compute the reaction forces, you should get that exact same applied force. Okay. Okay. Next, in green, I've highlighted the places where we had our fixed support, right? And so even though we're externally we're not applying a force at nodes 1 and 4, there are some forces here that are being applied from the support to the structure in order to keep it in static equilibrium, right? Because we're applying a net force of 3,000 going to the right on node number 2, right? And so to oppose this, our supports here have to apply basically an equal and opposite force in total in order to make sure that the net force on our structure is 0. Okay. And so if you add up all the forces here, you do minus 1,800 plus 3,000 minus 1,200, you should get 0 because that's, the sum of all the forces is equal to 0. Right? And so when you compute the reaction forces, you should get non-zero forces wherever you have a fixed support. Okay. And then finally, we have node number 3. Node number 3 there is just chilling. So, there's no forces that are acting on him. So node 3 just kind of transmitting the forces between the fixed supports and the applied force. Okay. All right. Any questions on any of that? Okay. All right. So that's truss problems in 1D, right? So now let's start talking about truss problems in 2D. Okay. So we'll start it today, and then we'll probably finish it up over the next two classes, I believe. Because the jump from 1D to 2D is actually quite complex. So there's kind of a lot involved in that. So I don't know if you guys had this experience too, but in my a lot of my classes when I was in college, and we whether it be like heat transfer, fluid mechanics, structures, or something like that, we do the vast majority of the problems in 1D, and the professor will be like, oh, the extension to 2D and 3D is easy, you just apply it over and over again. I don't know if your other professors have kind of swept things under the rug like that, but it's never easy to go from 1D or 2D. It's always pretty complicated. Okay, so I'm not going to sugarcoat this here. I'm not going to say that this is going to be easy. In fact, it's going to be very tedious. But it's necessary because what we've done so far are 1D problems, which are kind of nice for learning the basics, but it's just not very it's just not very useful in practice because we don't live in a 1D world. We live in a 3D world, right? And so ideally, what we'd like to do is apply finite elements in ultimately 3D, but 2D is going to be a step to get there. Okay, but there's a lot that we kind of have to do in order to get there. Okay, all right. So first thing I want to do is to kind of draw you a picture here. Right? And so let's say that we have a truss element. Okay, but instead of being flat on the ground, we're going to angle it up at a certain angle. Okay. And so I'm going to draw a horizontal line to denote our x-axis. Okay, that's our usual horizontal axis. And then the angle that it makes with that axis, I'm going to define as theta. Okay. All right. And so all this is pretty standard so far. So you have a rod, you tilt it up, then you have the angle through which it's tilted up. Okay. Okay. And so in addition to that, I'm actually going to draw one more line here, and I'm going to draw this line down the barrel of our element. Right? And what I'm going to tell you here is that this blue line right here is actually going to be a different coordinate system. Okay. And that coordinate system I'm going to denote with a hat. Okay. Right. Right. And so it's a coordinate system just like our usual XY coordinate system, except it's going to be rotated. Okay. Okay. And so now we have kind of two coordinate systems that we need to kind of worry about here. So we have in red, we have a regular X, so that's kind of our standard XY coordinate system. And then we have this rotated one that's been rotated to be in line with the element. Okay. Okay. And so let's give these guys different names so that or let's give them actual names so that we can actually refer to them, right? And so the first one I'm going to give the definition for is our rotated one. Okay. Right. And so the name for our rotated coordinate system is going to be the local coordinate system. Okay. All right. And so the reason we give it the name local is that it's local to whatever element that we're considering. Okay. Okay. And whenever we have the local coordinate system, we're going to denote it with a hat. Okay. Right. And so we have x hat in the picture right here, but there's also going to be a y hat, which is going to be perpendicular to that element. Okay. All right. And so the local coordinate system is nice because what it will allow us to do is it will allow us to basically use the exact same element stiffness matrix that we've had before, right? Because if you notice, from our spring and from our truss, we formulated that element stiffness matrix, assuming that our x-axis perfectly aligns with that element. Okay. Once we start getting into 2D and things start being rotated, our x-axis is probably not going to be aligned perfectly with that. But we can define a local coordinate system, which is just unique to that element, where it does align with it. So we can define our element stiffness matrix in the same way that we've done before. Okay. Okay, and so that's the local coordinate system. And now in red right here, what I have is what's called the stationary coordinate system. And so sometimes I'll refer to this as the global coordinate system, but I try to avoid using the word global because we use global to denote our global stiffness matrix. And so these are coordinate axes that don't change, right? So hence the name stationary. And this is necessary because, once we start having a ton of different elements, we can't just keep rotating willy-nilly, right? We need to have something that we can refer back to so that we can kind of analyze complex structures within kind of the same frame of reference, okay? And so this is used as a reference. Okay. And when we compute our global solution, which is the displacements at all the nodes, it'll be within this stationary coordinate system. Okay. Okay. Right. So those are our two coordinate systems there. And so basically the game that we're going to play right now is, how are we going to transform between one coordinate system to another, right? Because, just to kind of give you a preview of what we're going to do, we're going to use the local coordinate system to formulate the element stiffness matrix because we already know how to do that. And then once we've done that, we're going to rotate that element stiffness matrix into the global system, and so that we can actually combine it with some of the other ones. Okay. Okay. Any questions on this so far? Okay. All right. So let me go right down kind of where we want to go. And so formulate element stiffness in global system. Then rotate